quick review. Our Moody diagram, what we're going to need. So if you've got it, it's in the notes that I uploaded for today. You should pull that up. We have it here on the screen, but
I can share mine with
okay.
whenever you need it.
Okay. And it's this complicated figure that has two dimensionless numbers. That you find the intersection of whatever it is you have for relative roughness and Reynolds number, and then read across to get the friction factor. All right, and so in general we have that this friction factor we're thinking about things that we might need to calculate or be given. There's a bunch of things involved, either in the Reynolds number or in the relative roughness. And what we're going to do today is go through some problems that rely on the Moody diagram and of various types. Yes?
What specific page is the notes? Are the notes?
Yes, it's in the modules. It says solving pipe flow problems, notes.
Okay. Now someone was asking.
It's the module for chapter 8.
Okay, they got it.
Okay, good. All right. And so I'm going to step through. What we'll find there are 3 types of problems. I said this last time. That get harder. And I hope to get through an example of these latter 2. I think that we can skip over the first one. And if we had sort of a generic kind of problem, where it's steady flow in a pipe between locations 1 and 2, so we're given a bunch of things, and we're asked to find let's say that we're asked to find the downstream pressure. And what I intend to do is use this same sort of generic problem, steady flow, no change in elevation, and then vary the things that are given and the things that we're going to try to find. So not changing the pipe diameter or not changing the elevation, then the energy equation simplifies to and then, like I said last time, we have this equation for the head loss. You combine the two of these to get, and I'll just call that a difference in pressures from upstream to downstream. And if you look at, so say we're given P1 and we want to calculate P2, or we're just wanting to calculate the difference in pressures, depending on how the problem's given. So all the rest of this stuff is either given or on the Moody diagram. And this is a type 1 problem. So all you really need to do is know how to use the Moody diagram, take the things that are given to you, and you can use it to calculate what you're asked to find. Nothing really complicated in that. It's really these next two sorts of problems where the complications arise. All right, so let's go on to just think in general about that next kind of problem, the find the Q, or sometimes called the discharge problem. We know what the pipe's made of, and we know its diameter. We're given the pressure drop per unit length, and we're asked to find Q or V or both. And if you again write the energy equation, it hasn't changed any. But the problem now is that we have two unknowns. And to solve this problem, we'll do one of these. actually, you can think of it as two unknowns, F and V, and two equations. This is one of our equations, and the Moody diagram is in effect is our second equation. That is, it relates the thing that we want to know, the friction factor, to the things that were given. And so it can be solved, this problem can be solved, but it can't be solved explicitly. It has to be solved iteratively. And we'll do an example of that. But before that, just to point out what happens in the third type of problem. So now imagine we're given now we're asked to find the diameter and v, the velocity. In this problem, if you think about in the discharge problem, if you think about the two non-dimensional numbers, the relative roughness and the Reynolds number, we don't know the velocity, so we don't know the Reynolds number, but we do know the pipe roughness and the two things that we need to know to find the friction factor, but not the other one. In this problem, since we don't know the pipe diameter, we don't know either the relative roughness, that is epsilon over d, or the Reynolds number. So we have to guess if we were to somehow be able to guess values, we'd need to guess both to get a friction factor. Here, we'd have to guess the Reynolds number because we don't know the velocity, but we do know the relative roughness. Okay, so this problem's even harder to do than this is called I think most often referred to as the design problem. It's the one that you may come across in professional work. That is, when you're figuring out what sort of pipe diameter is needed to supply a particular flow. All right, so that's what we're up against in this type 2 and type 3 problem. Let's start off by doing a typical type 2 problem. I can stop here and ask her questions too. Break point. if there are any yet. Now, I point out that there's a table in the text where if you know what the pipe is made of, you can determine the epsilon value, the equivalent sand grain roughness or the equivalent roughness height. I have gone and looked in that table for cast iron pipe and found that that's in feet. That's like the characteristic size of the bumpiness on the walls of the pipe. Okay, and so we're given all of this and the head loss over that length. Okay. So if we write, you can write the energy equation. Okay, so let's write the energy equation. And this is a case where the elevations are the same, the velocities are the same. So we simplify all of that to and if you look at this, what you'll see is this equation doesn't really help us because it doesn't, we're given this and we're not asked to find the difference in pressures. So the energy equation isn't much help. All right, but if, for instance, if we were asked to solve for one of the pressures given the other, then we could use it, this equation for that. But what we do have is the Darcy-Weisbach equation. And we also have the continuity equation. Is it acting up again?
Yeah, the recording one. The Zoom one's good. But
It's only been in my office.
yeah, it's not focusing.
It's not focusing?
Nope.
Oh. Okay, so let's, okay, that's the one that's not attached to the
Not attached to Zoom.
the
The
tripod.
Zoom one's good.
Okay. What's that?
I was saying Zoom is good.
Okay. And I will switch it for the, I have a third one at home.
Mm-hmm.
So there might be another one up in the office.
I wonder.
Oh, I have a third one in the office upstairs, yeah.
Okay.
So, a fourth one at home.
I
So
can go
I'll-
grab it.
If you want, yeah, you could grab it out of my, so those who are on the Zoom call,
Yep.
Ring's not available until she gets back.
Just focus on those two panels.
Okay. Okay. All right, so Darcy-Weisbach equation, and I was saying that the continuity equation gives us the relationship between velocity and flow. So once we find the velocity, then we can use that, or rearranged, we can use that to give us the flow. Yeah, because that's actually how we're going to do it, is find the velocity and then calculate the flow. And there's a strategy for these type 2 problems. Since we know the relative roughness, we can take a guess at F what we're going to do is we're going to guess an F and then once we know F, we'll use this equation with the things we're given to calculate V. Once we know the velocity, we calculate the Reynolds number. And then get an updated F and repeat the process. And we will say that we're done when the update that we get to the F doesn't change much from the previous value that we had from previous value for F. All right, and like I said, our starting point for the friction factor will come from the known relative roughness, assuming that it's fully rough. All right, so let's put that into practice. But before we do that, let's make it convenient to find the velocity once we've calculated the F. Rearrange our equation plug in the values. All right, so all of this is just a number. In fact, we'll get that V is...
Would gravity be 82.2?
Is it really? It would be, yes, it would be. Thank you very much. Because it is an English unit. So we're going to need to update that with my 32.2. And so, McKenna, if you could, or whoever's got a calculator, give me all of this. Okay, and then, once we know the velocity, then we'll find the Reynolds number. Okay, so like I said, where we start is with a guess at this F, assuming it's fully rough. We have to calculate what the relative roughness is. And just for the sake of making it easier on us, we're going to just assume that our relative roughness is this nice round number, 0.002. Okay. So, the place to start, like I said, is the Moody diagram with an initial guess for F. So we go to the Moody diagram. And look at the 0.002 line. And like I said, we're going to use the assumption that it's completely rough. That is the right-hand side of the Moody diagram. And we need it a little smaller on the one on the screen here so we can read it over to the left to see what the friction factor values are. I actually used the version in the book, which has what we would say that it's just eyeballing it, it's about 0.025. Will you believe that? People out on Zoom, to make sense, 0.025, yeah? Give me a hands up or thumbs up if that's what you get on your version of the Moody diagram.
I'm not seeing any. Okay, I got Farah. Gave me a thumbs up.
Okay, I'll take one. And from then, we then calculate the velocity. And you calculate that. Casey, you got something?
I got 5.07.
5.07 sounds reasonable. Yeah, yeah. And that's feet per second. And that's a nice number because then that lets us get the Reynolds number. 5 times 0.5 is 2.5 times 10 to the 5th. Once we've got our, so we've guessed F, used that to calculate V, then calculated Reynolds number, and now we come back and we can calculate the friction factor again. We go back to the Moody diagram with that 2.5 times 10 to the 5th. That's going to be about right there. And you see, okay, that might be a little bit less, but just a little, a little bit, but not much. Okay, we're still on the part of the, we're just barely into the transition region. So I'd say that it comes back to the value that we used the first time, and so we're done. And we've gotten our answer that the velocity is 5.1 feet per second. Calculate this and get one. Okay. 1.0 cubic feet per second, which is our answer. So this is a relatively easy one, and with this good first guess, which you'll get most of the time, because most of our problems are particularly water flow with fairly large pipes. We get Reynolds numbers that are relatively large, and so this initial guess, using the fact that it's completely rough, will be a good guess. All right, so yes.
Would you mind explaining again how you got the F from the diagram?
Sure.
And do you mind just doing it on here?
Doing it on where?
From the diagram.
From the diagram, sure, I'm happy to do that. Yes, I'm going to, here we're going to turn it around for me.
Yes. Just, yeah.
Oops.
Well, that should be okay.
Okay.
There's the mouse for you to.
Let's see, do you see the mouse? Lost it.
Right here.
You know, on Zoom, there's supposedly a thing where you can make the mouse show up better. It's some sort of feature. I'm not. All right, so we are wanting to find the friction factor when the Reynolds number is where the Reynolds number is 2.5 times 10 to the 5th. So it is a little tricky to read this Reynolds number. Note that the grid is on it's a logarithmic scale, so if you look at the bottom, the number that's right above the S in Reynolds number, that's 1 times 10 to the 5th. And the vertical grid line that's just to the right of it is 2 times 10 to the 5th. And so on, 3, 4, 5, 6, 7, 8, 9. And then you come to 10 times 10 to the 5th, which is the same as 10 to the 6th. In our case, we're wanting to do 2.5 times 10 to the 5th. So you go over one grid line and then in between the 2 and the 3. So we want something in the middle here, and we go up. The arrow is going up until you find the point 002 line. So it's right in this neighborhood. And then from here, then you read across to the left, going horizontally to somewhere in between 0.02 and 0.03. So that's why we came up with 0.025. Why we started with 0.025 was by assuming that we were in this fully rough region, which is to the right of the dashed line. They call it complete turbulence on this diagram. And in that region, the friction factor is constant regardless of the Reynolds number. So you can just take whatever relative roughness you have and then read over, and we got a friction factor that might have been just a little bit less, maybe 0.024, but very close to what we came up with the second time. And that's because we were barely into the transition region. See, if we had gone to lower Reynolds numbers, then the friction factor would have increased to higher values, and we might have needed another iteration. I hope that helps. On to a type 3 problem. This is similar in what we're given, with one little change. I'm using galvanized iron which, looking up that epsilon in the table, we get 5 times 10 to the minus 4, and this is also English units, so 5 times 10 to the minus 4 feet, using that standard value for the kinematic viscosity. But this time we're given, rather than asked to solve, we're given the flow rate and the head loss and the length of pipe, 18,000 feet. And asked to say what kind of pipe, what's the smallest commercially available pipe that will give you this much flow with that much head loss over that length. All right, so I'm going to do a similar sort of thing where we guess enough and iterate, but the process is a little more complicated because we don't know what the relative roughness is, because we don't know diameter. So the suggestion is to just start at a reasonable guess for the F. And a reasonable guess for F. If you look sort of in the middle of the Moody diagram, so you start there. And then if you look at the Darcy-Weisbach equation, and I've rewritten it, instead of velocity, I've rewritten it to use the flow rate. So I've substituted in V equals 4Q over pi D squared. So instead of V squared, I've now got Q squared so this is a version of the Darcy-Weisbach equation using, only works for circular pipes. If we're given our Q, this is the convenient way to, and if you look at it, we don't know the F, but everything else here we're given. Except for, we don't know the D either. So if we guess an F, then we're given the head loss. If we guess an F, then this equation can be used to calculate a diameter. And so, just rewriting this, we get so I've just exchanged the put the H sub F, instead of on the left, I put it in the denominator and pull the D over to the left-hand side of the equation, which would be D to the fifth, and then take the whole thing to the 1/5 power. All right, and if you then put in the values, and it's 0.3. Careful with the G, mess that up before. And I'm going to instead just put the whole thing to the 1/5. Okay? And I'm not going to ask you to calculate that because it's going to take a while. And what I get is 0.7171 F to the 1/5 is our equation for D as a function of F. All right, so that, once we guess F, then that gives us D. All right. Likewise, we can use this equation and this equation, combine the two of those, substitute for the put the, let's see, I put Reynolds number in there and I get, so I combine these two and get Reynolds number is okay. So I put the known Q in there, and that gives me a relationship between V and D, and then plug that into here to get a relationship between Reynolds number and diameter. this is what you end up with. So that's our second equation that we can use, where this one is our first equation. So the way this works is you guess an F, then calculate D, and use that D to calculate Reynolds number. And then we also need one more. Let's see, where is it? And with the D, so then, once we've calculated the D, we then get relative roughness and put these two together to update our value for our friction factor. And that's the process. So that's first step, second step, and our third step is here. And rather than doing the number crunching, I've done that with an initial guess of 0.03. Then get a value for D, get a value for epsilon over D, okay, so we'd start off with 0.03, use that equation, would give us an estimate of the diameter is this. Calculate the relative roughness. Use those two, go to the Moody diagram, update our friction factor. And do we need to iterate again? Yes or no? I see McKenna nodding yes. We've got 3 people in the audience. We'll get, that's Kyle, is that Kyle? No.
Me?
Yeah.
Audrey.
Andre, sorry. Andre, what do you think? Yes, iterate, yes or no?
Oh,
Just pick one. We're getting late.
Yes.
What's that?
yes.
Yes. So, Casey, yes. So it's unanimous. Why do you know? Because this is where we started with. We guessed initially 0.03. We've been able to quit if our updated F was close to 0.03. And so the fact that they're not that close to one another means we do have to iterate again. So we would then start over with a new, we take this F and it becomes the next F, and then we run through the process again. All right, so when we do that, and the nice thing is that because the F is raised to the 1/5 power, changing the F here by 30% gives a change in the diameter that's much, much smaller on a relative basis. So the F doesn't change much at all when we plug it into this equation. And it is because of that F raised to a low power that's responsible for that behavior. And now these two D's are very similar, so you get the same value for the relative roughness. You get a very slightly changed value for the Reynolds number when we plug it into that equation. And when you go to the Moody diagram a second time, you get the very same value that you had or on the previous iteration for F. And since these two are close to one another, then we're done. And the pipe diameter that we come up with is this, which is the equivalent of 5.28 inches, and then you have to there is not a limitless variation in pipe diameters, and I think you go from 4 inches to 6 inches is what you can get in commercially available pipe. So from here you'd choose D equals 6 inches, and you're done. All right, so that's the most complicated kind of problem. I don't think we have one of those on the homework, but it is called the design problem. So in the working world, you are faced with problems like this. Maybe on the PE you might have one. Okay, we'll leave it there. Answer any last minute questions? All right then, we'll see you back here, or all of the links are present for the test on Friday.